Let's stay focused a little bit better today. We have talked about vectors in 2 dimensions. There will be only one thing that we talk about today that we didn't talk about with 2 dimensions. Okay, and I'll say that to the very end. First, I want to remind you how we represent vectors. We have 2 different ways to represent them. I will graph them up here, but I don't really think that it's necessary for you to graph them in your notes. Okay, and then we'll go through magnitude and unit vectors and all of that stuff that we talked about in 2 dimensions. Okay, so I want to remind you that we use these chevrons to notate a vector. And now that we're in 3 dimensions, we're going to have an ordered triple instead of an ordered pair. Okay. Oh, that was terrible. Like I said, you do not have to plot this in your notes. But remember, when we talk about a vector, we would go to that coordinate. So -1, 2, 4, and we would draw our vector from the origin to there. Okay. Whoops. Okay. Octant number. Emma, what octant would this be shooting to? 2. Be octant 2. Okay. Now, if I gave you a vector, if I gave you 2 coordinates and I wanted the vector PQ in standard position, how do we calculate that? What?
Distance formula?
We wouldn't need the distance formula. That would just give us a number. Would you agree?
Oh, yeah.
Okay. So we just want the vector. Almost. Mm-hmm. In a particular order. We have to take terminal minus initial. Terminal point minus initial point in order for us to get the vector. So in this case, our terminal point for PQ would be Q. So we would take -2 minus 1. And we would take 0 minus 2. And we would take 5 minus 3. And so vector PQ would be -3, -2, 2. Are you wanting me to plot this?
Yeah.
Okay. So -3 for the x would be back here. And -2 for the y would be here. So here's our parallelogram. And then we would go up 2. So we'd be in octant 3 for that vector.
So why don't you just like plot P, plot Q?
That would be a vector, but if I would want the vector in standard position, we would want to write it in component form so that we could plot it at the origin. Okay. When vectors are in standard position, then we can find the angle in between vectors. We can find their magnitude. We can find all sorts of different things about them. Okay. As a reminder, there is a second way we represent vectors. So we're probably the most comfortable looking at vectors in the component form with the chevrons. But we had vector I and vector J that we use. Well, now if with our third dimension, our unit vector in the z direction is vector k. All right. So the vector 3, negative 5, 2 would be the same as 3i minus 5j plus 2k. And those of you who were complaining about alphabetical order yesterday, things are right with the world. We have IJK in order.
IJK.
I'm just kidding.
I don't think I'm
I have never ever thought of that when teaching this. Now I'll never forget it. Okay, and remember the I, the J, and the K are always bolded, okay, because they represent a vector. I is the vector 1, 0, 0, J is the vector 0, 1, 0, and K is the vector 0, 0, 1. Okay. Anybody need more time to write this down? It's getting kind of noisy in here, so I'd like to move forward. Okay. All right. So we are going to go through a series of slides where I'm going to ask you to think about how did we do this in 2 dimensions, and then I will write down how we're going to do it in 3 dimensions. Okay. So we're going to recall and then adjust for 3 dimensions. All right? Not going to be that bad. A lot of the stuff is the same. So let's talk about magnitude of the vector. Magnitude of the vector. First of all, when we're finding a magnitude, what are we actually finding? Emily?
The size of it.
The size in what regards?
Like the length.
Okay. Magnitude is the length of our vector. Okay. In 2 dimensions, if we had the vector v1, v2, then I'll remind you, this symbol stands for magnitude.
Oh, right.
How did we find it?
Oh, yeah, that stuff's long.
Yeah.
It was like
Inverse tangent.
That would be the angle.
wasn't it the fractions?
No, we're not quite yet to the fractions. So this would make like a right triangle, right? Component horizontal, component vertical. So we're talking about the Pythagorean theorem. So the square root of v1 squared plus v2 squared would be solved for the magnitude. Okay? Ah. Emma Ralston asks, now do we have v1, v2, v3? Now we have 3 components, and our magnitude is still calculated by the square root of v1 squared plus v2 squared plus v3 squared would be the only difference. We just need that 3rd component underneath the radical, just as we did 2 days ago with our distance formula. That's essentially what we're finding, right? We are finding the length, the distance between initial and terminal. So we're going to find the magnitude of -1, 2, 2. If you'd like to start working ahead of me, that is fine. But we are going to find the magnitude of -1, 2, 2. If our magnitude is negative 1, 2, 2, then we have the square root of negative 1 squared plus 2 squared plus 2 squared. I don't know. Parentheses. So our magnitude would be 3. We'd have the square root of 9, which is 3. Okay? Yes, you will have a calculator in your hand, but I do want you to keep these as reduced radicals if they don't end up being nice like radical 9. Okay? Radical 12, I would expect you to reduce down. I don't want decimals, I want reduced radicals. All right. Now, we did calculate the direction with our vectors in 2 dimensions. Well, in 3 dimensions, our direction isn't quite as simple. So I am not going to ask you to find the direction. What I do with my calc kids is we find the direction from the x-axis, the y-axis, and the z-axis. So what are all the different angles we can measure from that vector? But we're not going to worry about that today. Okay? I do want to remind you the different operations that we can do with vectors. So, we'll start here. Go ahead and write down vector u and vector v. Okay, I'm going to give you maybe a minute and a half to calculate u minus v and 5v plus 2u and compare it to your neighbor. I'll give you a minute and a half.
Oh, thanks. So if I give you problems like this on your test, well, that would be my hope. Like, these should be the easy points, right? I mean, out of everything that we're going to do, these are about as simple as you can get. So please be careful and don't rush yourself on these types of problems. Okay, don't try to do too many things at once. Okay, number one's not so bad because we just have 1 minus 0, negative 2 minus 5, and 3 minus negative 2. Right? But down here, what I fear is that we're going to try to do too many steps at once and then get our numbers all jumbled. Okay? So I would highly suggest doing one thing at a time. So distribute your scalars first before adding your numbers together, just to make sure that you don't get did what?
5 times 5 is 5.
All right. Are we okay with that? Okay. Next, a unit vector. First of all, its meaning. What is a unit vector? Okay, a unit vector is a vector with magnitude 1. And on your test in chapter 6, I asked you to find a unit vector in the same direction as a particular vector. Okay? So I might have given you the vector 3, 5, and I said, hey, find a unit vector in the same direction. Oh, yes, this time. But the calculation is the exact same. So I'm curious as to what that calculation was.
Was that the one where it was like one? Wasn't it the one over there? Equals something.
So, or you can write it as V divided by the magnitude, however you wish to write it. But if our magnitude of V is magnitude V, and we divide by it, it forces us to have a vector of magnitude 1. Okay? Like if you find this magnitude, they would cancel out to be 1. Okay? So what's nice is our formula is the same for 3 dimensions. Our magnitude just has 1 extra step in it than before. So I want to go back to our example. We had the vector of -1, 2, 2. Remind me, what did we calculate that magnitude to be? Okay. So our unit vector in the same direction, remember if we take a scalar and we multiply it to a vector, it's going to change the length of the magnitude of the vector, but it's still going to be going in the same direction. So we would have -1/3, 2/3, and 2/3. Since these two are scalar multiples of each other, they are parallel vectors. Now, how many times do you get a magnitude that's a nice integer? Once in a while, right? So if you do have a radical, please make sure you rationalize each of the components. Okay. All right. Is this coming back to you?
A little bit.
Yes.
The dot product. This is one of my favorites. The dot product. And remember, I told you there's 2 different ways to multiply vectors. One is the dot product. Tomorrow, we get to look at the second one, the cross product. Okay, so the dot product. If I have 2 vectors, and I take the dot product between them, we multiply the components and add them together. And so we end up with getting just a number. Okay, we get a scalar for the answer. So in 3 dimensions, what are you going to guess?
It's like kind of the same, but different at the same time.
What's going to be different about it?
There's a third number.
That you're adding.
Okay, we just have that third component to multiply and tack onto the end. Okay, so we're still going to get a scalar. We just have 3 products to multiply and add.
That's why I added the little tail. Oh, really?
Okay, please write these down. Okay, so in order to calculate this dot product, we're going to take negative 1 times 3 plus 2 times 2 plus 2 times negative 1. Which, ladies and gentlemen, would be I haven't pushed you too hard yet. Okay? I would say everything that we've done today, we've done in the past. It's just in the third dimension, which really hasn't changed that much about our work. Okay? So I'm going to give you one more familiar item before we talk about something completely different. Okay? The angle between vectors. Some of you have been trying to allude to this formula, but didn't quite know where to fit it in at. The angle between vectors. It deals with a cosine and a fraction. If I'm finding the angle between two vectors, do you remember what goes here? The dot product is in the numerator. And then the two magnitudes multiplied to each other in the denominator. So you would need to find all of this and then punch in your calculator, which would be in degree mode, inverse cosine, so that you can solve for the angle.
Ew, that's awful.
Okay, so we are going to find the angle between vector u, which is 1, 0, 2, and vector v, which is 3, 1, 0. Okay, we need three calculations in order to be able to do this problem. We need the dot product and we need each of the magnitudes. Okay? So if you're sitting in pods 1, 2, or 3, I want you to calculate the magnitude of u. If you're sitting in pods 5 and 6, I want you to calculate the magnitude of v. And if you're sitting in pods 4 or 7, I would like you to calculate the dot product. Sorry, I didn't think of what was left. Thank you. Thank you, Riley. All right, pods 1, 2, 3. What is the magnitude of u? Radical 5? Okay. Magnitude of v? Radical 10. And the dot product? Okay. Now, when you type this into your calculator, since you have a product in the denominator, don't forget parentheses. So in your calculator, you would need to take the inverse cosine of 3 divided by the quantity, radical 5 times radical 10. In degree mode.
Oh wait.
Do you get 64.9? Make sure you're in degree mode. Make sure you're getting that product in parentheses. Okay? Now, there's a couple special things that could happen. What is true if the dot product is 0? Then the angle is what? This would be 0. But the cosine of 90 degrees is 0, which means our vectors are orthogonal. Okay? So if the dot product is 0, you don't have to go any further. You know that we have orthogonal vectors. The angle is going to be 90 degrees. Okay? What about if theta is 0 degrees or 180 degrees? What does that mean? What's true about our vectors if they're going in the same or the opposite directions? They're parallel vectors. Okay, well this is orthogonal means perpendicular. Okay. So if you're going in the same or opposite directions, we would consider those to be parallel vectors. Now, what did I just tell you about 5 minutes ago about parallel vectors? They are blank of each other.
They are blank. Opposites.
They could be opposites.
They're nice.
Okay, so these two are parallel vectors because they are scalar multiples of each other. Okay? Whether it be positive or negative, if two vectors are scalar multiples of each other, they're going to be parallel. So the vector 1, 2, 3 and the vector 5, 10, 15 are parallel vectors because they are scalar multiples of each other. Why am I making a big deal of this? It does sound important. So, this is the last thing that we're doing. And this is the only new thing that we're talking about today. Technically. In 2 dimensions, we calculate slope, rise over run. In 3 dimensions. Okay. There's 3 dimensions. We can't make a nice fraction for slope. Okay? So if I give you 2 points and I ask you to determine if they are collinear, we can't just like calculate slope and see if they're the same. Okay, we have to do it a different way. All right, so vectors give us the option of calculating 3-dimensional slope. Okay, in order to determine if points are collinear, we are going to have to create 2 vectors. Okay. Can we create 2 vectors with 3 points?
Yes.
Okay.
we take 3 points and we create 2 vectors, they're going to share a point, right? Okay. So if we create 2 vectors and our vectors are going in the same or opposite direction, if they are parallel, if 2 parallel vectors share a point, they're going to make a line. If 2 vectors that are not parallel share a point, they're not going to make a line. Okay? Do you understand the pictures that I've drawn up here?
Yes.
That was like rude, yes. Yeah. Like giving me attitude here. Okay. It might have been like the combination of everybody's yes, like, yes, Mrs. Holman, move on. Let's do this. Okay. Did you write down these 3 points right here?
No.
Okay, go ahead and write those down because that's going to be our example. What we need to do is we need to determine if our 3 points create 2 parallel vectors or not. And if we have 2 parallel vectors that share a point, they're going to be collinear. If we have 2 vectors that are not parallel and they share a point, they will not be collinear. Okay? What I am going to ask you to do is explain to me how you know they're collinear or not. So you're going to have to actually like give me an explanation, and if you don't give me an explanation on Friday, you're not going to be rewarded full points. Okay? So, does it matter which vectors we create?
No.
No, let's just make it easier on ourselves. Let's create PQ. Don't forget terminal minus initial. If we create PQ, terminal minus initial would give us -2, terminal minus initial, terminal minus initial. Okay. And I just like things to be in order. So I am going to create QR. The vector QR, terminal minus initial, would give us, I think +4, right? 0 minus -4. 6 minus 8. And 7 minus 1. Okay. So first of all, are these parallel?
Yes. They are.
Yeah.
Okay. So since -2 times PQ would equal the vector QR, then we know that PQ is parallel to QR.
That's actually improved. No, I've seen it. You remember those?
I mean,
Down
you,
the tree?
yeah, I remember them.
Okay.
Okay. Yeah.
No, not necessarily you guys. I do remember.
Well, if you take this vector and multiply it to negative by -2, you get this vector, right? Which means they're scalar multiples of each other. If you'd rather write, like you could, I'm just trying to not write as many words, but since PQ and QR are scalar multiples of each other, then we know that PQ is parallel to QR. You could say that also. Okay. Okay. Okay, and since they share a point, then P, Q, and R are collinear. Okay, so you need the 2 pieces. You need to tell me that they're parallel or not, and that since they share a point, we have our collinear points.
But what you wrote down before was fine.
Yes, yes. This would be if you wanted to use words instead of symbols.
Got it.
You know what I mean? Okay. This right here is really the only new concept
Okay? So make sure you practice everything with 3 dimensions, but please don't skip over this problem. I will tell you right now, well, I've already told you, there's going to be one on the test. Okay? So make sure you understand how to answer it. Okay? All right. Now, you didn't get as much time in class to start your homework. That's okay. I think you can handle it. It shouldn't be a very long assignment. Tomorrow, we will take our last set of notes in pre-calculus ever.
And then we're gonna have a party.
Yes.